today I'll start with the laser rate equation. Last class I have discussed the lasing condition. Okay, so in the laser hull now there is an first the electron will injected, then from those electrons the photon will produce, but there will be a multiplication phenomena. From two photon will be inside the device, and from these two photons the four number of photons can be produced from the laser, so that it can produce the stimulated emission. So if there will be the stimulated emission as well as the spontaneous emission. There will be stimulated emission and spontaneous emission. Now, so I will relate the two different equation, and the equivalent condition will equate those two equations. So there is one equation and there is a one more equation. So what is the N is the number of electrons generated per unit volume, injected per unit volume, and number of photons produced per unit volume that can be related with the phi. Okay. So you are giving some driver current, that diode driver current, you are giving some diode driver current, so that you can get an injected electron, right? So the d phi dt is the photon rate, and the dn by dt is the electron rate. So how much for the rate of the photon over the time, the number of photons produced over the time, and number of electrons are produced over the time. So d phi dt. So the photon, how the photon can be produced from the device? For one, for the stimulated emission, due to the stimulated emission, due to the spontaneous emission, the photon can be produced. But if there is a reflectivity inside the device, due to the reflection, some photon will be lost. Okay. So the total number of photons are there inside the device is the stimulated emission photon, spontaneous emission photon, and the photon loss. So these are equivalent to a rate of the photon per unit volume, right? So stimulated emission photon, the photon associated with the stimulated emission, that can be defined as a C and phi. What is the C? C is the coefficient expression expressing the intensity of the optical emission and the absorption. So that due to the absorption and the photon, that is related to emission as well as the absorption. So C is the coefficient, and we know that N is the how many number of the electron are injected per unit volume. So stimulated emission also related to N and the coefficient and the photon. Okay. The spontaneous emission rate. Spontaneous emission rate, that can be defined as RSP. And the photon loss, there will be a loss of the photon, that's why the minus sign is there, the phi by tau ph. The tau ph is the photon lifetime. Phi, you know the photon. Okay. So this is the photon rate per unit volume, d phi by dt. And now come to the electron rate, dn by dt, electron rate. So the electron, there will be injection of the electron, okay, and then the spontaneous recombination and the stimulated emission. So whenever you are providing the driver current, so then only they will get some electron. This is the injection electron, and the recombination. Due to the recombination also you can get the some electron. Recombination means the electron will come from upper state to lower state. So then also there will be electrons in the ground state. Okay, and the stimulated emission. Okay, so electron can be related with the stimulated emission means there minus. So some electrons are producing the photon. Okay, so there will be a loss of the photon, loss of the electron. Okay, that's why there is a minus sign, right? So some electron will be recombined in the ground state, so this will be the minus, and the some electron will be responsible for the stimulated emission, so there will be a minus sign. So whatever number of the electrons are produced, okay, injected, from those electrons, some electron will be responsible for stimulated emission, and some electron will be responsible for the spontaneous recombination. Okay, so the how many number of electrons are there, so those will be responsible for mainly the stimulated emission. Okay, so the total injected electron J by QD, J is the current density, okay, Q and D, D is the distance of the specimen, the minus N by tau sp again at photon lifetime, total number of electrons, this is related to the spontaneous recombination, right? That the stimulated emission, this is the same for this equation and this equation. So that's why the sum with electrons are responsible stimulated emission. So that's why this in the electron rate equation, the minus given, same will be reflected in here. Okay, the minus C and phi, that will be subtracted from this equation, and that will come to the here C and phi. I hope it is clear. So how can you relate the photon rate and the electron rate equation? Now, suppose we have to determine everything as the lasing condition. When the the stimulated emission should be occur. Okay, when the point where the stimulated emission should be occur. Okay, at the threshold condition, at that moment where the lasing has not, the stimulated emission did not start. Okay, the stimulated emission not start at that moment. Okay, that moment the total number of photon will be zero. The rate of photon per unit volume will also zero. Okay, then the spontaneous emission rate is also zero because only the moment where the injection of the electron take place. Okay, at that moment the photon is also zero. The rate of photon that can be, if it is zero, you can write as a d phi by dt greater than zero. And the spontaneous emission rate, this we have considered as a zero only. Okay, so if you substitute the first equation, that photon rate equation, if you substitute the first equation, then if the phi is equal to 0, so what was the first equation? The d phi dt is equal to c n phi, and the other two terms are there. So if the d phi dt you give 0, then and RSP is 0. Okay, so it was the RSP and minus phi by tau ph. It was like that. If this is 0 and the phi is RSP is 0, then C and phi is minus phi by tau ph. C and phi minus phi by tau ph greater than is equal to 0. From here you can calculate the N, the threshold. The threshold moment, how many number of the electrons are injected. Okay, that NTH by 4. Right? Now, again, so the threshold current needed to maintain a steady state condition is found the electron rate is under steady state. So for steady state condition, one laser is just start. Okay. So when the laser is just start. Okay. The spontaneous at this moment the spontaneous emission will be start. Okay. At that moment, what will happen? Suppose the number of electrons that will be whatever injection in the number of electrons are injected, those will be responsible for photon. Okay, at that moment, the electron will be transferred into the photon rate. The electron rate will be transferred into the photon rate. So that steady state condition, the dN by dt is equal to 0. If we substitute the second equation, V dN by dt is equal to 0, okay, and your r is equal to 0, and if you put instead of n, if you put the 1 by ctpa, okay, so if with the second equation, if you write 0, then this will come, 0 is equal to jth by q. So j I have replaced with the total. So if you remember, recall this one, it was like that, jth by q d minus nth by tau sp and minus uh, c and phi. It was the minus c and phi. As the lasing condition, there is no phi also. So this spontaneous image is also 0. The C and phi is 0. Okay. And the J I have replaced with the TH, JTH by QD minus, and also I have replaced by NTH by tau SP. Okay. If you put the, if you substitute the NTH value from here, NTH is 1 by C tau PH. Okay, if you put the NTH value, if you substitute this one, you will get this equation. After that, you can put the NTH value, right? So this is the threshold condition when the spontaneous emission starts. That means you have to give this much current density so that this much electron will be generated. So this much electron will be responsible for the spontaneous emission. Okay, this much electron will be responsible for the spontaneous emission. I think this thing is clear. Okay, so when the suppose electron is injected, there is no communication of the electron. The threshold condition, the dN by dt is equal to 0. That moment the electron rate is not changing. Electron is constant. Okay, electron rate is electron is not changing with respect to time. That's why dN by dt is equal to 0. And if you substitute this one, you will get. So this is the moment. If you give this much threshold current, the nth amount of the electron will produce. So those electrons will be responsible for the spontaneous emission. At that moment, spontaneous emission will start. Now, if you put this value in the first equation, you will get one more equation. Okay, so then is the laser operation beyond the threshold. Okay, laser operation beyond the threshold. So, so if J greater than JTH. Now, the equation 1 and equation 2, if you substitute equation 1, so here you can see one equation is this one, Cn5 plus Rsp minus tau pH is equal to 0. One equation is this one, and one equation, this is a photon rate equation, and electron rate equation is J by Qd minus n tau Sp minus this one. Okay, right? So instead of tau sp, so there you will get one equation for tau sp from the previous slide, that JTH is equal to, in the form of the JTH you will get one equation, right? The NTH by tau sp, one equation you will get. So in the so if you equate these two equations, and if you substitute these two equations, you will get a this one. You can see, so this J is here only. This J is here only, and the one more JTH is there. So one more JTH means, instead of tau Sp, I have substituted the value for tau Sp, and I have written the this equation. So you will get the this one. This is the threshold photon. This photon produce the steady state photon density. At that moment, the photon density which is responsible for stimulated emission as well as the spontaneous emission. So when both the stimulated emission and spontaneous emission started, at that moment how much photon will be produced. Okay, this is the phi s. Okay, again I am telling. So you will get one equation. So already you got one equation. So that JTH is equal to something. You got one equation, and these two equation, you know, one is the photon rate equation, one is the electron rate equation. Now you can, if both is equal to 0, then you can substitute these two equation. Okay, if you suppose add this equation, you will get one more equation. So from that equation, if you replace the tau Sp value with the this one JTH form, the JTH equation, then you will get a this one. This is the equation, the threshold steady state photon density. Okay, when the after the stimulated emission and the spontaneous emission. So that means for making the stimulated emission and the spontaneous emission, you have to give some amount of the current, and corresponding amount of the current you will get the phi s. This is the, at that moment, the minimum photon rate. Okay, minimum photon density. This is the phi s. Now come to the external quantum efficiency, right? So external quantum, so in the device it has the one is the internal quantum efficiency, one is the external quantum efficiency. So the internal quantum is, that is totally related to internal thing of the device. Okay, external quantum efficiency, how much amount of the photons are coming out from the device due to the injection of the current. Okay, due to the injection of the current inside the device. Okay, so whenever the external quantum efficiency formula will be there, there will be, this will be in the term of the power and in the term of the I. Internal quantum efficiency, that will be in the form of the photon and in the form of the electron. The number of photons emitted per radiating electron hole pair, per radiated electron hole pair recombination above the field. So whatever electron hole pair will recombine, so those recombination will not produce the photon which will come out from the device. Suppose some 100 amount of electrons and holes are recombined, so you should get the 100 amount of photons from those, from the device. But you are getting the 80 amount of the photons from the device. So this gives the external quantum efficiency. So in some device, if the internal quantum efficiency is more, but however, if there will be reflectivity, so you will not get the higher external quantum efficiency. Is increase in the photon, you can relate the external quantum efficiency like that, increase in the photon to the increase in the current. Okay, the rate of the differentiation, the decrease in the photon and increase in the current. So that you can do the d p by h phi equal by d I by. So whatever photons you are giving, so due to the this photon, if there is a change of the power, okay, that will the dp by dp, that the change in the power, okay, change in the power per photon, okay, the change in the current per electron, okay, this is the related to external quantum efficiency. If you substitute this one, you will get q tp by eg by d1. Okay, so this h phi you can replace with the eg, and e I have written here q. Okay, so q by eg into dp by di. Okay, again you can put the eg is equal to hp by lambda, hp is equal to hp by lambda. Okay, we substitute this one, you will get a this form. Okay, 0.8065 lambda dp by di. So the main definition is that again I am telling. So the change in the power per incident photon, okay, per generation of the photon, and the change in the current per number of electrons. Okay, this can be given the how much amount of the current you are providing for generating the electron, and this is ratio between the how much amount of current you are providing for generating the electron and how much amount of the power you are getting for producing the photon. Okay, so this is related to external quantum efficiency. Normally, if the internal quantum efficiency is 60 to 70%, see the external quantum efficiency will be 50 to 40%. That's why I am telling that the internal quantum efficiency and external quantum efficiency both will not be same due to the device structure and orientation. So, if you want to calculate the efficiency from the graph, you can calculate like this. So suppose for case of the laser diode, it will be for case of the LED, you can get a linear graph. But for case of the laser diode, you will not get a linear graph. So first, the stimulated emission will be there. For sorry, spontaneous emission will be there. This like LED type emission. So for that, this shape is one linear and there will be another linear. So two slopes are there. So this change in the power due to the change in the current, this is for the spontaneous emission. At the stimulated emission, you will have the more number of the photons, that more number of power you will get. So the slope will be changed at that moment. The threshold point, the slope will be changed. This is the threshold current. So at that moment when the stimulation emission starts, okay, you will get one current. So if you want to calculate the slope dp by di, so you will get a less value. So here if you want to calculate the dp by di, you will get a high value. So the difference depends in so that's why the efficiency is like that. The change in the current with respect to change in the power. Okay, change in the current power with respect to change in the current. Okay, so that formula is like that 0.8065 lambda d p by di. Okay, so lambda you know which lambda laser you are providing, you are getting the laser light you are getting. So from lambda you know, then if you measure this curve, the IP power versus current curve. So from that you can calculate the d pi by di and you can get the value, right? So this is about the laser efficiency and how can you calculate the laser power and power from the graph. So this is about this thing. So I think you like my channel and you like, share and subscribe my channel. I think everything is clear whatever I discussed. In the upcoming lecture, I'll start with the photo detector. Thank you.